You can add the stress and the strain to the same graph. So in here, this is your time, and this is your strain. Keeping in mind that these two have different axes, yes? So you can't really keep them like this. So what you can do is you can do right click, and then you can do select secondary axis. See? So now you have, let me take this chart to a different page. Okay, this, you can play with it so that you can do better quality. Axis titles. This is your time, T in second. This is my stress. This is axial stress, sigma in kilopascal, we agreed. And this is your axial strain. To make things align better, I'm going to change the axis for this so that they are both. Maybe I can make this, what, 235. I have 90, so I'm just going to make it maybe 4.5 in here. This is going to remain. So I'm going to make it 70. I'm going to make it 10 maybe, then 80. You can do any scale you want really, as long as it's consistent. So you can see in here, we're losing a little bit of the resolution. I would rather make it a little bit better. So in here I'll do this 20. 25. Again, you got the point, but in here I just want to change this to axial strain. And this is epsilon, and we agreed that this is microstrain or micromillimeter per millimeter. So again, one is how you basically present the data, two is how you analyze this data for each sequence, and how you can calculate the frequency. The frequency is basically you're counting how many peaks you have, or how many cycles you have in the duration. So this is more like 3, 4, 5. So maybe take this period and see what is the time that it took for that 5 cycles, or take the period for this 1, 2, 3, 4, 5. So the blue line, and take the period for that 5 cycle. So one thing you can do is stress over strain. You can determine the stiffness. The other thing is to take to do the phase angle. And we agree that the phase angle for the mix is equal to time lag so stiffness E star is equal to stress amplitude over strain amplitude. Phi mix or phase angle is equal to time lag or divided by time per cycle times 360. So how do you get the time lag? You try to determine where is the peak located, and where is the other peak. At high frequency, these two peaks are going to get closer. At low frequencies, they're going to get farther away to indicate that you have a more viscoelastic behavior. So again, you have to really try to more like draw a line in here, draw a line in here. You can see that there is very small time increment that you're going to get for the time lag. You divide it by time per cycle, which is total time divided by the number of cycles times 300 degrees. The higher is this number, the more viscous the material, the lower is this the number, the more elastic is the material. Okay? So now you're going to get, let's count how many sequences we have. So we have 1, 2, 3, 4, 5, 6 temperatures, or 6 frequencies corresponding to 6 curves. Okay, so you're going to basically get the dynamic modulus for each frequency, and then you're going to plot a log E star versus log frequency curve for the testing temperature of 54 degrees centigrade. Okay, so that's first problem. Okay, you can see in here additional details on how to do things. Calculate the stress and the strain. Stress is equal to load cell divided by area. Strain is equal to LVDT reading divided by LVDT length. Then you're going to basically do things together, so then you have to use the secondary axis so that you don't get the two scales to be far away from each other, and you get the two scales to be on top of each other. Calculate the loading frequency for each of the 6 loading sets, and then basically determine the dynamic modulus. How do you do that? Maximum stress, minimum stress, take the difference, maximum strain, minimum strain, take the difference, time per cycle, time lag, so that you can also get the phi angle. And then you can plot these two. Usually E star versus frequency is easier to get. Once you get to the phi mix versus frequency, usually it's a little bit harder because the time lag is not very easily obtained. So that's basically, again, the first problem. Second problem, I mentioned to you that it basically involves a little bit more modeling. And the model that we're going to fit in here is called sigmoidal. Okay, so this is the data that we have. I'm just going to copy it to Excel. Now, if you try to plot this data, just dynamic modulus versus frequency. Okay, this is how it looks. Usually we use log scale for the dynamic modulus and log scale for the frequency. And you can see that now things start to look a little bit more you can see that things now start to look a little bit more horizontal or linear for these data, for this data. Okay? So now in this problem, I'm asking you to do something that is a little bit different, which is to fit a model. These data, each set of data, was obtained at a different temperature. So you can see at high temperature the stiffness will be at high temperature the stiffness will be low, at lower temperature the stiffness will be high. So what we're trying to do is to basically develop a model that will basically capture or that will reference all moduli to the same temperature. Okay? So now if we look at the temperatures that we have in here, you can see that we're dealing with 10 Fahrenheit, 40 Fahrenheit, 70, 100, and 130. Okay, that's again at the testing temperature. So what we're going to do is going to use a shift factor so that we can basically shift the data from the other temperatures to the temperature of 70 Fahrenheit. So in here, I'm going to do this. So there we go. So this is the temperature, and this is the shift factor. It's commonly referred to as A. Okay, we have 10, 40, 70, 100, and 130. We agree that the shift factor at 70 is going to be 1, but for other ones, it's going to be higher. Let's make it 100, for the other temperature. So now you take to each, this is called reduced frequency, or FR, and it's equal to each one of these frequencies times the corresponding shift factor. Okay, so let me do that at 4. So all these are C3. Whenever you use that $sign, that means that you are actually fixing the cell. So this is C4. This is C5. So this is, again, what I'm trying to do is something called shifting. This is 7. Okay, so now instead of using the original frequency, I'm going to change this to the reduced frequency. So you can see that now things start overlapping. So if we can come up with a set of shift factors where things will start aligning better. So in here I'm going to do maybe 200, and this is more like you can see that I'm getting more like the data to overlap. So that's the first part of the analysis, which is to get the data to overlap, and here we probably have gone too far. Okay, so now you can see that this is called a sigmoidal model. Okay, where you have this very much like S shape. This is called a sigmoidal model. You can see that I'm doing it initially by hand, but at some point you may be able to do it automatically. We're going to see how that would work. So this is the first part. Okay, these are the shift factors that I got at each temperature, and these are the shift factors that will help me shift the data so that I can get it all to overlap with the 70 degree Fahrenheit. So this is the 70, and now I'm getting an extension of the 70 in all both directions. This is the colder temperatures, and this is the warmer temperatures. Okay, so now how can I develop a model for this data? We've learned how to develop a model for a linear function. Let's say that you have this data for x, and let's say that you have this data for y. I'm going to use 5.3 times, okay, plus 7.5x times x. So let's say that you were given the following data. Okay, I'm going to use 13, 21, 25, 33, 45, 47, 60, 68, 75. How do you fit a model for this data? Anyone who remembers? Forget about these. I just use these for guidance, just to come up with something that makes sense. So how do you fit a linear model for this data? You go to Insert, Data, and then right-click, Add Trend Line, Linear, and you select basically the equation and the R-square, yes? Yes? So now how is this process done? This process, and what is this process based on? This process is based on minimizing the square of error. What does that mean? what is the square of error equal to? If you come to this equation, this equation is linear equation, yes. So in here, A is equal to, yeah, sometimes the other way around, but that's okay, as long as we call it the right way. 7.8583. Sometimes they flip them, A and B. But this one is, I'm going to just assume, okay, so this is, I'm going to call Y measured, and this I'm going to call Y predicted. So what is Y predicted equal to? It's equal to Y A times X plus B, yes? And what is the error equal to? Or the square of error?
Predicted.
Square error. The error is equal to predicted minus measured, yes? Or measured minus predicted. That's basically your error. In here I'm doing the square of error, so I'm going to do to the power 2. Okay? And then I'm going to look at the sum of the square of error. So now let's assume that in here I'm starting with 3 and 1. Is this combination gonna give me the least square error in here? No, because we found that the combination that will give you that is really this combination, yes? But then how can we change these until we get the same answer by minimizing the square of error? You can do that analytically, because you can describe an equation between the error and your A and B. So you can develop a partial differential equation with respect to A, partial differential equation with respect to B, and then basically try to minimize them to solve for the values of A and B that will give you basically the optimum solution. Or you can use something called the solver option in Excel. How does the solver option work? You can say that I want to minimize what? I want to minimize the sum of the square of error, yeah? How am I going to do that? I'm going to do that by changing cell A and cell B. Okay? It's up to you if you want to define them to be positive or negative. I'm going to uncheck this so that they can be positive or negative, whatever they want. There are different methods you can use in here, and once you basically click this, you can use certain convergence criteria to basically reach to make sure that you get the right answer. But in here, I'm gonna basically just assume that everything looks okay. I'm just gonna start changing A and B until I get the minimum value. Let me do that, and voila, what did we get? We get the same answer that is obtained analytically, okay? So now we can follow a similar approach to fit the sigmoidal model. So the sigmoidal model has the following format. Log stiffness is equal to delta, alpha, beta, gamma, and this is log XR, which could be time or frequency. In our case, we're dealing with frequency. Okay? So now what we're trying to do is to find the alpha, beta, gamma, delta. Okay? So we can start with any combination of values that we want. We can start with any combination of values that we want. So now I'm going to do, so this is your measured E star, yes? I'm going to do another one that is going to be my predicted E star. And now I'm going to basically use the alpha. Okay, I'm going to use first delta, alpha, beta, gamma. Okay, so in here, these are symbols. You can assume them all to be 1, but eventually that's not going to work, you know that. So in here, to be able to use this model, I'm going to use this equation. and I'm going to define it. For the model. So I have delta. Notice in here that you have log, so we're going to take care of this log in a second. Okay, but delta plus alpha over 1 plus exponential of beta plus gamma times log, you can log 10 times the frequency, which is reduced frequency. Okay, close. So now in here, I'm finding what? I'm finding log E star. So to find E star, I'm going to do 10 to the power, yes? So in here, I'm going to do, again, dollar signs, dollar signs, dollar signs, and dollar signs. And then I'm going to basically do this for the predicted. So if you can find a combination of alpha, delta, alpha, beta, gamma, that will give you a match between these values, then you have found your model parameters, yes? So now, how can I do that? Again, very much like I did before, I'm going to do the square error. Which is measured minus predicted. Or predicted versus measured. Doesn't matter because we're going to do the square anyways. Make things a little bit easier to see, I'm going to keep my summation in here. So you can see it's very high value. So let's try to first, and you can, so let's try to minimize this value first by changing the alpha, beta, gamma, delta, and see if we can get there. Let's do 2. Okay, so that's going up, not going down. So they are still too high. Let's try the, maybe there is going to be, do we have any value that needs to be negative? Delta, let's try minus 0.1. Okay, there are. Let's try to see if the solver also. The solver is very sensitive to what you use as a starting guess. But again, we're going to try it anyways. I'm not going to change anything in here, I'll just uncheck this and try to solve. Let's see. It did not really give me anything meaningful in here. So
negative value for delta?
let me do this 1 second. So in here, edit, add. I'm trying to develop a model between this data and this data. I'll probably need the model to be in points. What is the data? They're too small. It's too small. So this is going to be. So you can see it's too small. So we have to increase it. What do we need? We're getting this now to be too high. least a starting point. Okay, here we go. So you can see that again, this had to be negative. In other words, to basically get the match. You can do better than this, but the other thing that you can do is you can see. You remember these values? Okay. We did not really. We did them manually. Why don't we even throw them in and see if this will give me a better match between the two? So I'm going to change not only these, but I'm going to change those together. So let's see and solve. So here we go. See? So you can see that now we use the solver not to only do the model fitting, but also to do the selection of the shift factors. You have to be a little bit careful with these because the small ones will need to be a little bit with more digits. The larger ones can be okay, but these ones need to still have a large number of digits. Okay, so now this is the modeling for which? This is the modeling for the shift for the sigmoidal model. Now you can also do a model for the shift factors. Okay, so to be able to get the stiffness of the asphalt mixture, the stiffness of the asphalt mixture is dependent on two things, yes? It's dependent on the frequency, like we can see in that figure, but it's also dependent on the temperature. The frequency is captured using the sigmoidal function. The shift factor, we can develop another model for it to actually describe that relationship. Now to do that, this is the model that you need to use. You can follow the same procedure that I have in here, that we have just gone through. Okay, and this is the model. It's called the WLF equation. It stands for the name of the people who came up with it, Williams, Landell, Ferry. Okay, and this is the equation again to describe the relationship between the temperature and the shift factor. You can do it eventually just between A and T, or you can do it between log A and log T. If you use A and T, then your shift factor at the reference temperature would be equal to 1. If you're using log AT, log 1 is equal to 0. So it just depends on how you're going to plot it. What do I mean by that? If you plot these two in here versus each other, again, you can see that this value in here is 1. Actually, I made a mistake in here. Let me do this one step. You cannot change this as part of the solver, because this has to remain 1, yes? So let me use the solver again. So when I change, I have to select these two, and these 4. I cannot choose this one, because this one has to be 1. You cannot shift the 70, because your reference temperature is 70. And then I'm going to solve. So you can see now this one is 1. Okay? This cannot even be minus. So now, one thing you can do is, okay, so solver, I want to use this, I want to use this, I want to use these, but you can see in here it gave a numerical error, okay? But I want to make a constraint, then this, all of these have to be greater than 0. I'm going to use 0.0. Okay, it does not like these. There we go. These two have to be greater than 0, and these two have to be greater than 0. Okay, and then solve. So this is the answer now. So you can see that again, it goes down with temperature, and this is basically the one that gave us the minimum error. So again, we still are having a little bit of an issue fitting this part of the curve. It seems like we're doing a little bit better with the rest of the curve. It's just that in here, we're not getting a little bit of a good quality of it. But that's again, whenever you're doing modeling, you're not necessarily going to get all good data. So in here, if you do this, you can see that, okay, I'm getting all of that. The problem with this data is that you have a large value and you have very small value. This is why it's more common to do these kind of modelings in a log scale. And now once we get to the log scale, what kind of trend do we see? You can see that now log, so this is 1. If you want to do it as log 1, it's going to be 0. But you can see in here that it's more like relatively getting a little bit close to a line. Okay? So this is why this model was selected. So now again, this covers the first two problems. It's a little bit hands-on, I understand that, but again, I hope that you're learning a tool that you can add to your toolbox. The other one is basically the back calculation of the falling weight deflexometer data. We went through an approach for that, and the approach was based on developing a database using by running WinLaya several times, and I already gave you this file, so you can follow the approach in here. Most of the equations, they have already been included in here, so you can just use them directly and solve the problem. Okay?
Are we allowed to email you like big portions of this, like kind of where like we're getting all of our data from, instead of printing it off, all those test results off?
No test results. I don't want the. I don't want this data.
Yeah.
Yeah, I don't want this data. I only want the graphs.
Okay.
I may ask for the Excel files.
Yeah.
To get my print. So you can send me the Excel files by email, and email this way I can send them to the TA when he's grading. He at least can go back to your Excel files if he sees anything that needs to be checked. Okay. So in here. How are we doing in general with this? Again, some people get overwhelmed. I understand that, but others find it manageable. So on a scale of 0 to 10, who says it's more like 0 to 10 in terms of difficulty? Who says it's 10? You are getting there. Okay. Who says it's more like 6, 7? Okay. Who says it's 0 to 5? Is very familiar. Okay, you're very familiar with that. Okay. So again, 10 is if you need help, I can help you. Okay. But you need to get started because at least you need to start. I need to take it one step at a time. And again,